Good morning everyone. So, you are looking into the ion exchange separation processes, and in the last class we looked into the operating principles of ion exchange separation process. Now, in today's class we will just do the calculations relevant to the ion exchange processes, and then we will move to the next separation process, that is the electrophoretic separation processes. Okay. So, let us look into the theoretical calculations. Those are relevant for ion exchange separation processes. Again, you are going to have a column here, and the ion movement theory will be almost similar like solute movement theory in the chromatographic column. Okay. The ion movement theory will be almost similar to the chromatographic velocity form that we have calculated for the chromatographic column, and the ion movement velocity will be related as V divided by 1 plus 1 over epsilon E C R T divided by C T delta y by delta x times K E, okay, where y and x are equivalent ion fraction. In resin phase or in the solution phase, K E is a factor that includes the Donan exclusion and electroneutrality. Factor accounts for Donan exclusion and electroneutrality. If ion is excluded, then K E will be equal to 0. Excluded, K E equal to 0, otherwise K E will be equal to 1. Okay. Now, for counter ions, like A plus, B plus or D plus plus divalent or monovalent counter ions, K E will be equal to 1, and for co-ions X minus, K E will be equal to 0. For K A B, the equilibrium constant greater than 1, this is for the monovalent exchange. That means, you are exchanging a monovalent ion by a monovalent ion, or K D B multiplied by C R T over C T is greater than 1, that is for the monovalent divalent exchange. It results a shock waves. A shock wave, that means, for these values greater than 1, shock wave results, and as we have defined shock wave in the earlier class, that if a concentrated solution displaces a dilute one, okay, then it is a shock wave. And as we have talked about earlier, that delta y in case of shock wave, delta y by delta x will be written by this will be y a minus y b and x a minus x b. A refers to after and b refers to the condition before the shock waves. So, A is after the shock wave and B refers to conditions before shock waves. Okay. And in case of diffused wave, that means, when you are displacing a concentrated solution by a dilute solution, that means, in the case of regeneration of any column, Okay. In the case of regeneration of any column, you will be displacing the concentrated solution by the dilute solution. In that case, there will be gradual change of concentration and the mole fraction in the solid phase and in the dilute phase. So, therefore, delta y by delta x will be replaced by dy dx. Okay. So, in case of shock wave, this is basically exchange cycle or basically adsorption cycle. U S H is equal to V divided by 1 plus 1 over epsilon E. Epsilon is the interparticle porosity, C R T divided by C T multiplied by K E Y A minus Y B divided by X A minus X B, where the subscript A refers to after and B refers to before the shock wave. And in case of diffused wave, when you will be getting the diffused wave, when you will be getting the regeneration cycle. U diffused, let us say diffused will be velocity divided by 1 plus 1 over epsilon E C R T divided by C T multiplied by K E dy dx. Okay. So, these will be the velocities when you will be working with a shock wave, that means exchange cycle, and this is the velocity when you are talking about diffused wave or the regeneration cycle. And in both cases the resin and liquid stream, they operate under equilibrium. That means, the solute concentration in the resin phase or in the in liquid phase, both will be dictated by the equilibrium relationship. Okay. Now, I will just solve a problem for ion exchange column. Let us look into an example. Ion exchange column. It is basically an analysis of water softening cycle. Okay. What is this analysis? It is basically we wish to soften water. That means, we would like to remove calcium ion from the water, having 2 milliequivalent per liter of calcium ion and 9 milliequivalent per liter Na plus with superficial velocity of feed as 10 centimeter per minute, right. Okay. Now, we are using a 2 meter column. Column length is 2 meter and CRT, it is given that the total ions present in the resin is 2 equivalent per liter. Then first we have to find out, determine the feed period. Okay. That means, for how long you will be basically running the feed. Now, that we have to find out. Let us look into the solution. The C total is the total ions present in the liquid stream that we can find out. In liquid stream, and that will be 2 plus 9 is equal to 11 milli equivalent per liter, and epsilon E is given as 0.4, that is the interparticle porosity that is given as 0.4 in this particular problem. Okay. So, once you get the total ion concentration present in the liquid stream, you will be in a position to get the mole fraction of calcium ion in the feed, and that becomes 2 by 11 and it is 0.1818. Okay. And mole fraction of sodium in the feed will be 1 minus that. So, it will be 0.18, 1 minus 1818, it will be 0.8182. Now, V is the interstitial velocity that is given as superficial velocity u, right. We talk about u, interstitial velocity, V superficial divided by epsilon E, and this turns out to be 10 divided by 0.4 is equal to 25 centimeter per minute. Okay. Equilibrium constant of calcium and sodium, that is given as 1.3. Okay. And K CaNa CRT divided by Ct can be calculated. So, this is a given data, this is equilibrium constant is given. So, once you get that data, then you can calculate this quantity. This turns out to be 1.3 to 2 divided by 11 into 10 to the power minus 3. Since it is milli equivalent and this is will be equivalent, so you have to convert milli equivalent into equivalent, and this turns out to be 236.4, which is much greater than 1. Okay. So, we are talking about a shock wave that so based on this criteria we come to the conclusion that a shock wave is resulted. Okay. Now, let us do the further calculations. After the shock wave, Xa Ca will be the constant mole fraction of calcium will be same as that of a feed concentration. So, it will be same as Xf Ca, that is 0.1818. That means, after the shock wave you should get the same feed concentration that was going into the system, and Ya Ca is therefore calculated from the equilibrium relation, calculated from equilibrium relation. Now, if you look into the equilibrium relation, this becomes Ya Ca divided by 1 minus Ya Ca square. Ya Ca is basically the mole fraction of calcium after the shock wave in the resin phase. Okay. So, this will be nothing but K CaNa CRT divided by Ct Xa Ca divided by 1 minus Xa Ca square of that. So, this turns out to be just put the values 236.4, 0.1818, 1 minus 0.1818 square of that, and this is 64.2, and now if you can calculate the Ya Ca, it turns out to be 0.8827. Okay. Now, you will be in a position to calculate the things. So, resin contains higher concentration of, so therefore, the resin must be containing the higher concentration of calcium after the shock wave. Resin contains higher concentration of calcium after the shock wave. Now, you can get the value velocity divided by 1 plus 1 over epsilon E CRT divided by Ct Ke YaCa minus YbCa divided by XaCa minus XbCa. Now, YbCa is before the shock wave the concentration of calcium in the resin phase, there was nothing, right. Before the shock wave the resin did not contain any calcium. After you have passed the solution, it will be exchanging the calcium. So, before that it will be having a value 0, and XbCa, that means the concentration of calcium after the concentration of calcium in the liquid stream, it was also is equal to 0. So, now if you put the values, this becomes 25 divided by 1 plus 1.4 divided into 2, 1.1 into 10 to the power minus 2 multiplied by 1, Ke will be equal to 1, okay, and this is 0.8827 divided by 0.1818, and it turns out to be 0.0113 centimeter per minute. Now, the low velocity, this velocity is extremely low. This low velocity of the wave, ion wave, is basically because your resin has a very high capacity. Compared to liquid concentration, and it is selective for Ca2 plus. So, once you get the velocity, now you will be in a position to calculate the retention time. The retention time for the feed will be therefore 202 meter. So, it will be 200 centimeter divided by 0.0113 centimeter per minute, and it turns out to be 294.4 hours. So, it is quite high time. So, you can operate the feed, and you will be getting a concentration of calcium after the shock wave, that will be almost equal to 0. Now, the second part will be bed is regeneration cycle. Okay. Regeneration cycle, the bed is regenerated by 25% by weight of NaCl at superficial velocity 0.5 centimeter per minute. So, you have to find the time required to regenerate the bed. Okay. So, let us look into the solution. Once you get the the superficial velocity, you can convert it into the interstitial velocity by V superficial divided by epsilon E. So, it turns out to be 1.25 centimeter per minute, and rho L is given as at 25 degree centigrade, rho liquid is given as 1.194 gram per cc. Okay. So, you can convert 25% NaCl to equivalent per meter, equivalent per liter. So, 25% NaCl, it means 0.25 into 1.194 into 1000. This is basically density of liquid at 25% of NaCl divided by 58.4145, that is the molecular weight of sodium chloride. So, it turns out to be 5.311 mole per liter, and this will be 5.311 equivalent per liter. Okay. So, you can get an estimate of Ct, that Ct turns out to be 5.311 equivalent per liter, and mole fraction of calcium is equal to 0 as regeneration liquid is totally NaCl. Is totally NaCl. You can compute this value K Ca Na CRT by Ct in this particular case. It turns out to be 1.3 into 2 divided by 5.311, and this will be 0.49, which is less than 1. So, we will be obtaining, again we get a shock wave when material concentrated in Ca2 plus is regenerated, is removed with regenerated. The time required for time required of ion wave to go to the column exit can be calculated. Go to column exit is 200 divided by 1.25, that is around 160 minute. Okay. Now, Ya, when the ion wave passes, YaCa is equal to YbCa, is 0.8827, and Xca changes because my Ct is now changed. So, you can calculate Xca divided by 1 minus Xaca square of that is equal to Yaca divided by 1 minus Yaca square 1 over Kcana CRT divided by Ct. Now, if you put all the values, this turns out to be 130.92. You put 0.88, this is 0.8827, and these values we have already computed. Okay. So, Xaca it becomes 0.9167. That means, the liquid stream that will be coming out of the column will be rich in calcium, and it will be the mole fraction calcium will be 91%. So, before ion wave, fluid exits with Ct equal to 1.1 into 10 to the power minus 2 equivalent per liter, and Xbca 0.1818. Okay. Now, immediately after the wave, the fluid exits with Ct 5.311 equivalent per liter, and mole fraction is 0.9167. Now, this continues until the shock wave where Xca reaches to 0. This continues as shock wave where Xca reaches to 0. So, you will be having before wave, you will be having Ybca is 0.8827 and XBCA is 0.9167, and after the wave you will be having YACA is equal to XACA will be equal to 0. So, you can get the value of the wave velocity, the interstitial velocity. It will be, you just put it in the same formula as we have written earlier. And this turns out to be 0.656 centimeter per minute, okay, and the time required is 200 divided by 0.656. So, it will be around 305 minutes. Now, this time is about 145 minutes after the total ion wave exits. Thus, the solution with CT is equal to 5.311 equivalent per liter and XA 91.9167 exits for 145 minute. How did you get 145? That is 305 minus 160. Okay. Okay. Once we do the regeneration cycle, then we can go for the washing. Okay. So, the washing is basically, in case of washing, we are washing the whatever the sodium chloride that is there in the resin phase. The washing step has a velocity V is 1.25 centimeter per minute. Okay. Since salt in the void volume is excluded, salt is NaCl in void volume is excluded. Okay. In that case, Ke will be equal to 0 and U wash will be nothing but V, that is 1.25, and the time required is 200 divided by 1.25 is equal to 160 minutes. Okay. Now, you sum up all the times and that will be giving you total water softening cycle time. Okay. So, this gives a fairly good idea about the how the ion exchange column will operate and how the chromatographic column will operate. Now, in the then we move to the our next separation process that is quite important, and that is the electrophoretic separation method, and this method we utilize the charged properties of the biomolecules which will be separated. Okay. So, let us go to the electrophoretic separation methods, and the basic principle of this separation method is that the different rates of migration or different rates of velocity, different rates of migration of charged species under external electric field. So, if you have charged species, they will be having different charges. So, whenever this electric field is same electric field will be operated on them, their velocities, the migration velocity will be different. Okay. So, you will be getting at a particular location, you will be getting the one particular species at a time earlier different compared to other species, they will be coming later to at that particular point. So, you can collect a particular species earlier compared to the other species. So, that is why you can separate. Now, this is effective for most of the biomolecules. Why this is effective for the biomolecules? Because most of the biomolecules are charged in nature. Okay. Each of these molecule will be having a characteristic pH where the charged molecule is neutral. them has a pH where molecule is neutral. That particular pH is known as the isoelectric pH. Okay. Now, the now one can control the operating pH by adding the HCl or NaOH. So, you can add a few drops of HCl, the pH of the solution will go down in the acidic region. If you can add some drops of sodium hydroxide, the pH of the solution can go up in the alkaline region. Okay. So, therefore, one can control the operating pH and above the isoelectric point or below the isoelectric point. Okay. The operating pH can be above isoelectric point, we call it Pi. It can be below the isoelectric point as well. Now, if the operating pH is above the isoelectric point, the molecule is negatively charged. On the other hand, if the operating pH is less than isoelectric point, the molecule is positively charged. Okay. Now, based on this principle, you can make them charged. So, if you have a mixture and if you have an isoelectric having an isoelectric point with in the overall range of pH, let us say from 2 to 7, then if you set it operating pH around 5 or 6, okay, then you can have some molecules positively charged, some molecule negatively charged. Now, if you apply an external electric field, then in one particular port or cathode or anode, some molecules will be going, and in the other port some molecules will be attracted. Now, I will give you some compounds, a list of the compounds and their molecular weight and isoelectric pH at 25 degrees centigrade. Aspartic acid, this will be having a isoelectric pH at 2.77, lysine isoelectric pH 9.74, oval albumin, it is a protein, it has a molecular weight in the range of 43,000 to 45,000, it will be having a isoelectric point 4.7, BSA bovine serum albumin, its molecular weight is around 68,000 and it has an isoelectric point about 4.95. Okay. And myoglobin, another protein which will be having a molecular weight around 17,000, that has an isoelectric pH around 7.33. Cytochrome C, it will be having a molecular weight 12,000 and that will be having an isoelectric pH around 9.28. Okay. Now, the movement of the charged species under the external electric field, as we have already discussed earlier, this phenomena is known as electrophoresis. Okay. So, electrophoresis is the main electrokinetic effect which is responsible for this electrophoretic separation method. The movement of charged particles under external electric field. Okay. Now, you can calculate the electrophoretic mobility. And this electrophoretic mobility will be electrophoretic velocity per unit field strength. Okay. And if you remember, it is Z e divided by 6 pi mu r p for spherical particles. Okay. And in case of charged colloids, for charged colloids, the system contains a small amount of electrolytes dilute concentration of electrolyte solution, they carry appreciable current, and therefore, there is a redistribution of the charges around the charged sphere, redistribution of co and counter ions around the charged sphere. Okay. So, that means there is a formation of electric double layer. EDL. Okay. Now, depending on the value of, once you get the electric double layer formation, you can find out the Debye length. Okay. We have already done all these calculations earlier. Debye length corresponding to the concentration of electrolyte present in the solution. Now, if kappa times Rp is less than 0.1, Rp is the particle radius, then electrophoretic mobility is given as 2 epsilon naught epsilon zeta divided by 3 mu, and on the other hand, if kappa Rp is greater than 0.1, then u is given as epsilon 0 epsilon zeta divided by mu. This epsilon 0 is basically dielectric constant of water. This value is around 80, and epsilon is the permittivity in vacuum. And mu is the solution viscosity, and zeta is the zeta potential of the particle. We already defined the definition of zeta potential and how they will be measured in a liquid solution. Now, typical value of the electrophoretic mobility in free solutions will be in the order of 10 to the minus 8. Okay. So, this is the typical value of electrophoretic mobility. Mobility will be in the order of 10 to the power minus 8 meter square per second and volt for ions, and it will be less for protein, 10 to the minus 9 meter square per second per unit volt for proteins. Okay. Why it will be less? Because the proteins will be having larger size compared to the ions. So, therefore, they will be less mobile. So, the mobility will be at least 1 order of magnitude less. Now, let us look into the various complicating factors, those are associated with electrophoresis. With electrophoresis. Now, the first complication that arises out of Joule heating. The power, thermal power that is generated because of a flow of current is dictated by the Joule heating. Is P is equal to V times I, voltage multiplied by the current. So, it will be nothing but I square R, where R is the resistance, electrical resistance, V is the potential difference, P is the energy generated per unit time, that is the power, energy generated per unit time is the power, V is the potential electric potential difference, I is the electrical current, and R is the electrical resistance. Now, in this particular case, the Joule heating will be having two folds of problem. The problems those will be occurring because of Joule heating. Firstly is that I square R is undesirable because it leads to local fluctuation in the temperature. Okay. Local difference in temperature occurs. So, what? So, if the local difference in temperature occurs, there is a local difference in density will occur, because density is a strong function of temperature. This result to density difference. If the density difference is quite significant, the convection will occur, like the free convection will occur, right. So, convection occurs. So, therefore, the movement or the transport of the particle will be disturbed by the electrophoretic mobility will be disturbed by the convective motion. Secondly, the second problem that you will be getting out of it, that at high temperature, if I square R or the Joule heating is high, the temperature difference may be high, the temperature build up may be high enough, and at that high temperature the protein may be denatured. Okay. Now, so these two are the added problem complicating factors during the electrophoresis, and let us look into the convective problem much detail. Now, temperature difference, local temperature difference due to Joule heating, it leads to density difference. If the density difference is there, that leads to the buoyant effect, and whenever if the buoyant effects they overcome the viscous effects, then you will be having a natural convection, right. If it is more than viscous effect, then you will be getting the natural convection type of circulation. Okay. So, density difference can be written as so this will be basically lead to a non-dimensional number. The non-dimensional number, Grashof number, becomes very important. Becomes very important, and by looking into the value of the Grashof number, one can say whether the natural convection is dominant or whether the natural convection is not dominant. Okay. So, Grashof number is defined as the buoyant force divided by the viscous force. Okay. If the buoyant force becomes more compared to the viscous forces, then the natural convection will be dominant. Now, there are several methods are used to avoid natural convection, because if you use the electric field across the 2 points, whenever you will be having a protein solution in presence of electrolytes, there will be current that will be generated. So, I square R type of heating or Joule heating you cannot avoid. So, some kind of Joule heating will be always occurring. So, in order to avoid the deleterious effect of the Joule heating, there are some methods to be adopted. Methods adopted to avoid Joule type of heatings or natural convection. Number 1, efficient cooling reduces delta T and prevents thermal degradation. So, you can have an efficient cooling in your system that basically leads to reduces delta T and prevents thermal degradation. Secondly, electrophoresis is conducted at 4 degrees centigrade where water density is maximum. Electrophoresis is conducted at 4 degrees centigrade where water density is maximum. So, if you conduct the experiment at 4 degrees centigrade, since the density is maximum, the change in density will not be much. Okay. In that case, you can curb down or control the convection effect. Okay. The third method generally used is difference in plates, difference between plates H is kept small. Okay. So, if this difference is kept small, then the natural circulation because of natural convection can be prevented to some extent. So, therefore, electrophoresis is conducted in small tube or gel or membrane. So, electrophoresis is conducted in small tube or the material inside the tube is filled up by a porous gel or porous membrane. So, that the natural convection will be controlled. Filled up with a porous gel, or sometimes papers we call it paper capillary tube, that means it is very small diameter, etc. Now, introduction of gel or membrane, what it does? It prevents convection. Okay. Now, second complication that occurs in the case of electrophoresis is occurrence of electroosmosis. Occurrence of electroosmosis is another complicating factor. Now, there are fixed charges on the wall of gel or the chamber, whatever it is, and these, because of the fixed charges and presence of electrolyte, now with an external electric field, it leads to electroosmotic flow. In fact, we have already defined how the electroosmosis occur earlier, and the fluid movement by electroosmotic flow, electroosmotic velocity can be defined. Velocity will be V electroosmotic will be epsilon 0 epsilon zeta of the wall or the gel divided by multiplied by E divided by mu. This is the electroosmotic velocity, and the electroosmotic velocity is it reduces the separation, because it added with the electrophoretic velocity. So, velocity becomes more. So, if the velocity becomes more, then the residence time between two particles will be less. So, it hinders. So, what is the problem that will be arising out of electroosmotic velocity? Reduction of separation becomes a result. Okay. And this reduction, the extent of reduction is a function of geometry of the flow channel. Extent of reduction, it becomes a function of geometry of the flow channel. And of course, the harmful effect of electroosmosis can be prevented. The harmful effect of electroosmosis can be prevented if the wall is coated with a material, with some material that will reduce the zeta potential. If the zeta potential of the wall is reduced, then the electroosmotic velocity will also be reduced. Okay. And what is that material? Maybe methyl cellulose or some neutral material, okay, which is not charged. So, harmful effect of electroosmosis can be prevented if the wall is coated with neutral materials like methyl cellulose, which is a very low, resulting into a low zeta potential. So, therefore, the mobility due to the zeta potential or the electroosmosis, mobility due to electroosmosis can be minimized. Now, in order to get this idea, there are several configurations of electrophoresis has occurred. For example, gel membrane and paper gel electrophoresis, membrane electrophoresis, paper electrophoresis, and there is something called page electrophoresis. Okay. So, polyacrylamide enhanced electrophoresis. We will be looking into some kind of normal electrophoretic method separation in the next class, and we will be solving some problems also, so that we will see how the separation occurs during an electrophoretic method. Okay. Thank you.